Think about how we organize things every single day. Your grocery list, right? Or that to-do list that just
Mm-mm.
keeps growing. Maybe even like the shows you want to watch next.
Yeah, ordered collections, they're everywhere.
Exactly. And in programming, there's a really fundamental way to handle this. It's called the list. Welcome to the deep dive. We take source material, maybe articles, research, even your own notes, and we really try to boil it down to the essentials, the goal, give you that shortcut, help you get genuinely informed, maybe with a few surprising details along the way.
Mm.
And today, we're diving into lists, specifically how they actually work in the programming languages you probably use.
Right. And our mission here, looking at the sources, is to really unpack what a list is conceptually. Then look under the hood, see how it's built, how it's managed,
Okay.
and crucially, understand why knowing all this stuff actually matters if you're dealing with code or data.
Mhm.
We want these ideas to really, click and stick with you.
Okay, let's get into it then. When we say list, just at its core, abstractly, what is that?
Well, at its heart, a list is just an idea, an abstract data structure.
Yeah.
It basically represents an ordered collection, a sequence of elements.
So order matters.
Order definitely matters. And the key thing, conceptually, is what you should be able to do with it. The source material points this out. Accessing things, changing things, adding new stuff, removing old stuff, and just, going through everything from start to finish.
Right.
Traversal.
Right.
And part of that abstract idea, the ideal, is that you shouldn't really have to sweat the details. Like, oh no, am I going to run out of space? In theory, it just handles it.
Okay, so that's the perfect theoretical list. Flexible, ordered, no worries about size. But computers have real memory constraints.
Sure.
How do programmers actually build that? The sources mention a couple of main ways.
Exactly. When you go from the idea to the implementation, you usually start thinking about two main building blocks, linked lists and arrays. Linked lists, as the sources describe, they kind of naturally fit that flexible list idea. They use nodes, pointers. Adding or removing something just means rearranging those pointers. Size isn't really fixed. It grows and shrinks easily.
So they seem like a good fit. What about arrays?
Arrays are different. They're these fixed blocks of memory.
Hmm.
Super fast for getting element number 5, right? You just jump straight there using the index.
Right. Direct access.
But, and this is a big bitty, but the source highlights they have that immutable length,
Yeah.
fixed size. Once you create it, that's it.
Hmm.
And that fixed size, well, it reduces the practicality of the list, as the source puts it, if you try to use a basic array as your list.
Ah, yeah. Because you have to guess the size beforehand.
Precisely. You're stuck trying to predict the maximum number of items you'll ever need. Guess too small, you run out of room.
Uh-oh.
Guess too big, you've just blocked off a load of memory you might never actually use. Wasted space. It's that fixed capacity that's the real hurdle for flexibility.
Yeah, that sounds like a major limitation if you need something that adapts. So how did languages like, Python or Java solve this for their main list types? How do they get around that fixed size problem?
This is where the standard solution comes in, and it's really central to the source material. They implement lists using something called dynamic arrays.
Dynamic arrays, okay.
Think of it like this. It uses a regular array underneath, so it keeps that fast O1 access benefit.
Got it.
But it adds a clever mechanism on top to handle growth. It can expand when needed. And what's really key here, something the sources really stress, is that for many, many common languages, Python's list, Java's array list, C++'s vector, C#'s list, the thing they call a list, is under the hood a dynamic array.
Oh, interesting. So when we talk about list in Python, we're actually talking dynamic array.
Pretty much, yeah. For the rest of this discussion, following the sources, we can basically treat list and dynamic array as synonymous in this context. It's the workhorse implementation.
Okay, that simplifies things. So the dynamic array is the practical solution. What are the typical things we do with these lists then? And how does that dynamic array structure affect how fast those actions are? The source walks through the common operations.
Right. Let's break those down. First up, initialization. Just creating one. You can make an empty list, start from scratch.
Yeah.
Or you can create one that already has some items in it, pre-filled. The code looks different in different languages, obviously, but the idea is the same. Empty or with initial values.
Makes sense. What about getting at specific items or changing them?
That's accessing and updating elements. And because it's built on an array, super fast.
Yeah.
Accessing the element at index, say 100 is 01. It's constant time. Doesn't matter if the list has 101 items or a million.
Like going straight to a mailbox number.
Exactly. And updating an element at a specific index is the same. 01. You just go there and change it, access the element at index, update the element at index, direct and quick.
Okay, but adding or removing, I feel like that's where things get trickier. That's not always O1, is it?
Yeah. You're right, it's not. Inserting and removing elements.
Mm-hmm.
This is where the underlying array structure shows its less flexible side. Adding to the very end, appending is usually fast. We'll say O1 on average, more on that average bit later.
Okay.
But inserting or removing anywhere else. Middle of the list, beginning of the list. That requires shifting other elements around. And that's an ON operation. The time it takes depends on N, the number of elements you have to move.
Shifting. What does that actually mean? Like shuffling things in memory?
Pretty much. Imagine you have A, B, C, D, and you want to
Mhm.
stick X right after A in index 1. You need to make space.
Right.
So D has to move to index 4, C to index 3, B to index 2. Then you can put X at index 1. Same idea for removing. If you take out B, C needs to slide into B's old spot, D into C's old spot to close the gap.
Ah, I see.
The source uses phrases like move all elements after index 1 position backward for inserting, and move all elements after index 1 position forward for removing. And if you insert at the very beginning, you got to shift everything. That's why it's ON. Could be a lot of work if N is large.
Okay, that ON makes sense now. Lots of moving parts. What other common operations?
Well, there's iterating the list. Just going through each item one by one. You can do it by index, like for id and range.
Well, that's a gray.
Or often more cleanly, just iterate directly over the elements, like for item and my list.
Right, and joining lists.
Concatenating lists.
Yeah.
Sticking one list onto the end of another. And finally, the sources mention sorting the list, putting items in order. This is useful in itself, but it also unlocks other efficient algorithms later, like binary search or two-pointer techniques if the list is sorted.
Got it. Okay, we've covered the main actions and hit that ON cost for insertions and removals in the middle because of shifting. But you mentioned appending is O1 on average. Let's circle back to that. This must tie into the dynamic part, the expansion. How does that actually work? The source gives a simplified example. How does it grow?
Yeah, this is the really clever bit. The simplified mylist example in the sources breaks it down into like 3 key parts. First, initial capacity. You still have to start with some fixed size array underneath. The example uses 10. That's your starting block of memory.
Makes sense. You need someone to put the first few items.
Second, and this is super important, size recording. You need a variable, maybe called size or a size in the examples, that tracks how many items are actually in the list right now. Not the capacity, but the current count.
Ah, so size might be 5, even as capacity is 10.
Exactly. This size tells you where the real end of the list is, and crucially, it tells you when you're about to run out of space in that underlying array.
Okay, so when size equals capacity.
Bingo. That triggers the third part, the expansion mechanism. Right before you add that next element that would overflow the current array, the list expands itself.
How? Does it just magically get bigger?
Not quite magic, more like moving house. The source describes this process. First, you create a brand new bigger array. How much bigger? Often determined by an expansion factor. A common one used in the source is 2, so you double the capacity. If it was 10, the new one is 20.
Doubles it. Okay.
Then comes the expensive part. You have to copy every single element from the old full array over to the new bigger array.
Wow, everything.
Everything, from start to finish. Once they're all copied, you update the list's internal idea of its capacity to match the new array's size. Then finally, you add the new element you were trying to add in the first place into the now roomier array.
Whoa. Okay, so every time it fills up, it's like packing up your entire house, moving to a house twice the size, unpacking everything, and then putting away that one extra book you just bought. That sounds like a lot of overhead sometimes.
It absolutely is a lot of overhead. That copy operation, moving potentially n elements, that takes ON time. That's why appending, which we usually think of as O1, suddenly takes ON time when an expansion is triggered. It's a temporary but significant cost.
So it's not always O1.
Not strictly, no.
Yeah.
But here's the clever part. The reason we say O1, on average or amortized, by doubling the size each time, these big, expensive ON moves happen less and less often as the list grows. Think about it. You copy 10 elements. Now you have space for 10 more before the next copy. Then you copy 20. Now you have space for 20 more. Then copy 40, airbase for 40 more. The gap between these expensive copies keeps getting wider.
Ah, okay. The bigger the list, the longer you wait until the next big copy.
Exactly. So while one specific append might be ON, if you average the total cost of all the copying over a long sequence of appends, the cost per append works out to be close to O1. It's called amortized analysis. That big moving cost gets spread out, making the average cost cheap.
Okay, amortized O1. That makes a lot more sense. It's usually cheap, with an occasional expensive hiccup that becomes rarer over time.
Got it. So we've gone from the abstract list idea to linked list versus arrays, the dynamic array solution, the operations, the shifting, and now this expansion mechanism. Why should you, the listener, really care about these under-the-hood details?
Well, understanding this dynamic array stuff, how it actually works, it's pretty fundamental. It tells you why some things are fast, like accessing by index O1, and why appending is usually fast, amortized O1.
But just as importantly, it explains why inserting or deleting in the middle is potentially slow. Knowing this helps you choose the right tool for the jobs.
How so?
If you're building something where you constantly need to add or remove items from the middle of a huge collection, maybe a dynamic array, a standard list, isn't the best fit. That ON cost could really slow you down. Maybe a linked list would be better, even though accessing elements in a linked list is slower.
Trade-offs.
Exactly, trade-offs. But if you're mostly adding to the end and reading items by index, dynamic arrays are fantastic. Knowing how they work helps you predict performance, figure out why something might be slow, and just generally write better, more efficient code. It's about moving beyond just using the list to understanding how it performs.
Absolutely. So we've seen the journey, the abstract list, the fixed array problem, the dynamic array solution with its expansion trick, the cost of operations like access, insert, remove, iterate, and that key idea of amortized time for appending.
Yep. Covering the concept, the common implementations, why dynamic arrays are standard, how their operations perform, and the details of capacity, size, and that doubling and copying expansion.
Which brings us to a final thought for you. We know dynamic arrays have this occasional ON cost for expansion, and that middle insertions deletions are always ON due to shifting. So it makes you wonder, are there specific situations where maybe a linked list, despite its slower ON index access, might actually be the better choice overall? What kind of problem might make you accept slower access to avoid those shifting and copying costs?
It's a really good question, thinking about those specific performance profiles. And if you're curious, digging into the actual source code for list implementations of languages you use, that can be really illuminating, showing even more optimizations built on these core principles.
Definitely something to think about. Thanks for joining us on this deep dive into lists and how they really work. We hope this gives you a much deeper understanding next time you use one.